Okay, we're going to go ahead and start. We have, are you stretching or asking a question?
Yeah, I'm stretching.
Okay, so just want to make sure. We're going to go ahead and start. We're going to take a look today at the general senses. Only last week we looked at the different types of general senses as far as touch and pressure and pain. And today we're going to take a look at proprioception, and we're going to take a look at reflexes. So let's bring this up and down here to proprioception. In next week, we're going to take a look at the special senses, and the following week, which should be April 12th, maybe, I think, we will do brains and eyeballs. So if you're going to be here, you'll have a chance to do a little dissection. And if you are on Zoom, you'll get to watch, because I'll have a tray set up here to dissect as we go along. So, of course, you're always welcome to come in and slice up brains and eyeballs. We've got plenty of both. So now, proprioception. The last thing we talked about last week was awareness of sensations and how our bodies adapt. And our body, there are some things our bodies, some stimuli our bodies adapt to, like touch and pressure and odors. And there are other sensations that we don't adapt to, like pain and body position and body chemistry, chemistry of the blood. We never adapt to those. Body position is something that we're always aware of where we are in space. It has to do with the position of our arms and legs, hands and feet, whether we're upright, whether we're seated, whether we are flat on our back. We are always aware of our position. We're aware of the movement of our arms and legs. We know what we're doing when we do them. Proprioception is the term here for where are we? Where are we in space? And we have a series of receptors, cleverly called proprioceptors, located in our muscles, in our tendons, and in our joints. And they can tell us all sorts of things about movement of our limbs, movement of the muscles, movement of the joints. They can tell us all about how fast we're moving an arm or a leg when we're doing something, how much load we are applying to our muscles. Are we overloading our muscles? Are we lifting more than we should? And what are the limits of the movement of an arm or a leg or a hand or a foot? Now, all of this input from these proprioceptors are going to tell us where we are in space. That's the standard answer for a proprioceptor. What's it do? Well, it tells us where we are in space. But it's more than that. Not only does it tell us our position, proprioceptors tell us if we are moving. Are we moving our arms and legs? We're aware of this. We may not be consciously aware, but we're aware of it. And are we accelerating or deaccelerating? Are we moving an arm? Are we driving a nail with a hammer? And are we striking hard on the nail? Or are we tapping the nail? Are we throwing a baseball? Or are we, throwing something else? Maybe you're, I don't know, maybe you went to a wedding and you're throwing birdseed at somebody, or, maybe you forgot to take it out of the packet. You're just throwing a whole bundle of birdseed. Movement, acceleration. What kind of force do you apply to an action? When I pick up a model off my desk here, am I gonna slam it back down on the countertop on my desk, or I'm gonna place it down gently, or hopefully not drop it? The fact that these models cost hundreds and hundreds of dollars, and I'd end up having to pay for it if I deliberately broke one, probably weighs a little bit on my mind as to how I'm going to treat it, So, but it's movement and acceleration, meaning what kind of force are we going to apply to something? Are you going to tap somebody to, if you see, your grandma, are you going to hug her? Hopefully she's alive when you hug her. Are you going to hug your grandma? Maybe you don't like your grandma, so you don't want to hug her. When you hug her, you give her that, 3 feet apart hug, like, hi, grandma, glad to see you, and let go. Or you're really glad to see her. That's part of force, acceleration, and movement and position. It all ties in together. And proprioception is something that happens constantly. We are always aware of our position. We are always aware of our motion. We are always aware of our balance, and we're constantly adjusting our body. So that if we're standing upright, we stay upright. When we're moving, we accommodate the changes in the surface we're walking across so that we can continue to stay upright. We're monitoring up and down. We're keeping our eyes on a fixed, we're not aware of it, but we are always trying to maintain balance with the horizon, such as it is. We're always looking for a horizontal surface to tell us which way is up. And so regardless of the surface that you're walking across, you are adjusting. I've got 2 trip hazards over here, 3 if you count this elastic surface here that I walk on to release, that they put down here so we don't have to stand on the hard floor. But for me, it's because I'm clumsy, it's a trip hazard. It sticks up about 1 inch. Over here, I've got the cables that lead to the podium that I can walk into. So if I'm not paying attention and I detect this, I have to make my proprioceptors have to tell me, hey, clumsy, don't trip on the wiring. Don't trip on the floor mat. Whether you're, and this is just a simple example. I don't usually call myself clumsy, but the point is that you're walking across a rough surface. You're walking up the side of a mountain. You're on a trail. You are riding your bicycle over, sidewalk to concrete to asphalt, and there's all sorts of irregular surfaces there, and you're monitoring your position. You're not like, oh, I better monitor myself now. We're doing it automatically so that we can stay in an upright position to maintain our balance. This is why body position never adapts, because we're always changing. If you're standing still and not moving like this, even then you're sweating a little bit. But if you're standing still, that's not we generally don't maintain a position like that for long periods of time. We're always moving around. We're always adapting to that. That's why proprioception is so important to us, so that we can stand upright, not fall down, so we can move and move correctly. Okay. Like, let's say you decide you want to go for a hike in the park. You decide you're going to hike up Mount LeConte, and you are taking a trail that you've never taken before. And you have to adjust to the trail. You have irregular surfaces, you have smooth surfaces, you have steep surfaces that go up and down, and your muscles have to adapt to that. And we don't think about it. We don't think, well, okay, I'm going downhill now. I better use my hamstrings a lot more now so that I can maintain my balance as I'm going downhill. Oh, now we have to go up. I better use my quads. We don't think that. We'd never get anywhere if we did. It is an unconscious response here. And we have a constant interaction with the antagonistic sets of muscles, like antagonistic pairs like the biceps and the triceps, for example, or the hamstrings and the quads. you would use those a lot when you're walking, going uphill or downhill. So proprioception does all sorts of things for us. It's constantly adjusting to changes in our environment. Consider this example here. You're at Food City, and you're holding a bag open, in produce section, and someone's dumping apples into the bag. Now you're holding the bag up like this, you would hold it open like this. And someone has 5 pounds of apples and they dump into the bag for you to fill it up. Well, what's going to happen is no matter how prepared you are, your muscles are going to respond to the shock of the sudden 5 pounds of weight in the bag. Your arms are going to drop down to this position because they're not expecting, no matter how prepared you are, they're not expecting for this sudden weight. But then you will automatically bring the bag back up to where it was. Proprioception trigger within our muscles. The muscles have been stretched, and the proprioceptors inside our muscle cells, inside our muscles say, hey, I just got stretched, I'd better contract. And so even if your arms sag, you're going to bring it back up. Why? Because that's the position you started in. Proprioception is all about maintaining our position. So there are 3 types of proprioceptors. We have what are called muscle spindles that are found within the skeletal muscles. We have what are known as the Golgi tendon organs, which are found between the tendon and muscle itself. The Golgi tendon organ, you know that muscles are covered with a layer of connective tissue called epimysium. That epimysium slides into the collagen fibers of the tendon. At the junction of the epimysium and the tendons is where these Golgi tendon organs are. And they're going to be monitoring the movement of the muscle and the movement of the tendon. Then we have the third one, what are called the joint receptors, or the joint kinesthetic receptors. It's easier to say joint receptors. And they are mechanoreceptors. These are all mechanoreceptors that respond to being pushed and shoved and twisted and so on. These are in the joint capsules of all of our synovial joints that surround all of our arms and legs, at the elbows and the knees, and at the connections of the humerus and the ulna and the radius and all your phalanges. All of the synovial joints that have capsules are going to have these joint receptors. So this is a muscle spindle. It's embedded in the middle of a muscle. You can see the individual myofibrils there around the muscle cell. And what the spindle does is can tell us how fast we are moving a body part. Limb velocity. And which way are we moving the muscle, moving the arm? We can tell this by the contractions of the muscle. All muscles can only do one thing, they can only contract. So we can tell that we're contracting, and we can tell at the rate of contraction. So we know that we can determine the velocity of motion, and we are moving simply by getting input from these spindles, that our arms moving like this, for example, or you're waving your arm, or you're driving a nail, all these things. And you're driving a nail so that you don't exceed the strength of your arm or the movement of your arm. You're not generally not going to take your hammer all the way back like this and drive it down as hard as you can. So this is what the muscle spindle does. It tells us what our muscles are doing. The Golgi tendon organs, they're located, as I said, they're located right at the end of the epimysium before the tendons form. And these tell us what kind of load we're putting on an arm or a leg. Are we applying forces to an arm or a leg that going to exceed the strength of that arm or a leg. What kind of resistance is the muscle feeling? How hard is the muscle working to do something? Is it past its point of safely having some kind of motion? You know, what's going on with your foot or your leg or your hand or your arm? The Golgi tendon organs will tell you this. It'll tell you that we are probably at the point where we're stretching our muscles, we're pushing our limb past its safe limit. You know, perhaps we're going to dislocate our shoulder. Perhaps we're going to break a bone. So, I mean, after all, bones break before muscles will tear. Bones will break before tendons will tear because of the presence of all the collagen. But bones do break. And so are we overloading the muscles? Is that going to snap the bone? And then the joint receptors, or also called the joint kinesthetic receptors, they're embedded in the capsules. They tell us when we're moving our joints. They tell us when we're moving our joints past their limit. You know, when you hyperextend your knee, for example, or you dislocate your hip or your shoulder, something like that. You know, when we move outside of the limit of what the motion of the joint can be, many times when we do that, we end up fracturing the bone. Other times we dislocate the bone. It just depends. But this is where this is our warning to say stop. You know, unfortunately, in most cases, the warning to stop occurs just about the same time that the problem occurs. You know, so but it's trying to tell you don't do that. Now, there's two types of proprioception that we're aware of. We have what's known as non-conscious reactions. This means that we're not aware that we're doing this. We call this the writing reflex. We do this ever since we were infants, ever since we were learning to crawl and raise our head up. We have this writing reflex. If our body is tilted in any direction, you are going to raise your head or move your head so that your eyeballs are level with whatever horizon you see. So if you are, for example, you are going up on a ride at Dollywood, you're going up on one of the roller coaster rides, and as you get near the top, you're sitting back, and you're in your seat and you're tilted back like that. And yet, if you have your eyes open, valid point there. If you have your eyes open, you are unconsciously looking at the ground, looking at the horizon, so that you have your perspective of what is up and down. This allows us to control. This is how we are going to control our balance. This writing reflex always lets our eyes level up with the horizon, because that always tells us which way is up. Even if we were hanging upside down on the eagle, for example, over at Dollywood, you would still try to, if you had your eyes open, you would still try to focus on the horizon so that you know which way is up. This is a non-conscious reaction, not an unconscious. Non-conscious. We're not aware of it. We're not aware that we do it. It feeds into our cerebellum. The cerebellum is the back portion of our brain. And this is a brain. Let me put it on the camera here. Okay. This is a life-size model of our brain right here. These very large structures. There we go. These are the cerebral hemispheres here and here. And most of what we are and who we are is in this outer layer of the cerebral hemispheres. We initiate motor activity from these hemispheres here and here. Left, we have what's known as contralateral control. Left side of the brain controls the right side of the body. Right side of the brain controls the left side of the body. All initiated from here. Now back here, the second largest structure in our brain are these things here called the cerebellum. These are called the cerebral hemispheres. This is the cerebellum. The cerebellum here is responsible for maintaining equilibrium and balance and something that we like to call muscle memory. This is where we learn and train and practice to improve our actions. And we store memory of how to do things in the cerebellum. And so it's also intimately acquainted with position and balance. So our non-conscious proprioception, our writing reflex, sends a signal to the cerebellum so that we can maintain our balance. Now, the cerebellum is the area that's, and we'll talk about this in lecture, but the cerebellum is the area that's affected by alcohol or different types of pharmaceuticals that will alter balance. You know, an individual that has had too much to drink has difficulty walking sometimes, or difficulty in talking or movement, because the areas of the cerebellum that control balance and equilibrium are impacted by excessive levels of alcohol. So anyway, cerebellum is our control center, a major control center for balance. And with non-conscious proprioception, we send those signals there. And we learn this when we're learning to crawl. Once the muscles of a baby's neck are strong enough to hold the head up, when a baby crawls, they will crawl with their head upright. So they can, even at that age, they can find their horizon and have, know which way is up and down. They're not aware of it, but that's what they're doing. They're trying to find they're trying to maintain their balance. So this is the writing reflex right here. Doesn't matter what angle our body is located in, we will tilt our head. We will find our horizon with our eyes and level our eyes with the horizon. And this now, that then gives us equilibrium. It tells the inner ear where all our equilibrium receptors are located. It will tell the inner ear which way is up. So this is why we will do this all the time. Our bodies do this unconsciously. So now that is all non-conscious proprioception. We're not aware of it. Conscious proprioception goes to the cerebral hemispheres, to the cerebrum, the two large lobes on the brain. And so we have conscious proprioception. We are then aware of positions. We are aware of how we're seated or how we're standing or what we're doing. We're aware of changes. Some changes we're not aware of. We constantly are monitoring and adapting. Other changes we are doing consciously. So something else involving proprioception is what we call eye-hand coordination. Yesterday I said high-and coordination, so I'm getting better. Eye-hand coordination or hand-eye coordination. We control the movement of our hand with what we're tracking with our eyes. Eye movement watches an object and we move our hands. Perhaps we're trying to catch an object. Someone threw something at us. We're trying to catch it. We are not just trying to catch it, not just trying to hit it or knock it down, but to actually catch it. Hand-eye coordination. If I were to throw this marker at Cameron, would he catch it? Yeah. You didn't dive for it. You didn't. I'll give you another chance. Okay. There we go. He caught it. Good for Cameron. So we should dive for it.
Want it back?
Yeah, go ahead.
And do you want it combined or you want it separate?
I'll try it combined. Then you won't have to throw it twice. There we go. Okay. Hand-eye coordination, tracking it with your eyes, but controlling the movement of your hand. So you can catch it or at least knock it down, so you can track it. We have a very, very powerful reflex center in our brain, which we'll talk about next week, that helps us to control the ability to track objects with our eyes. But that's only part of it. The hand-eye coordination allows us to move our hand in so that we can not just track it, but to catch it. We do a variation on this all the time. Think about every time you drive, you come up to an intersection and you got traffic coming both ways. It's like pulling out from campus. You got traffic on both ways. Now, are you going to sit there and wait until there's no traffic within 5 miles of the intersection? Or are you going to, or are you automatically going to say, okay, that car is far enough away and that car is far enough away that I can go ahead and pull out and turn either way I want to go? Are you a 5 miler?
I'm terrified of driving, so I like to wait.
And that's perfectly understandable. Because what your brain is doing is processing the information of how fast the cars are coming, how far apart they are from each other, how far apart they're going to be from you. And you are processing that. And in a way, it is still hand-eye coordination, because you're processing whether or not you can pull out safely, and not get rear-ended. So, or not, or you just wait until there's no traffic, and some days, some days I'm very bold when I pull out, and some days I'm just I'll just wait, because, I'm tired. I don't feel like engaging in, some serious driving. I just want to sit till there's nobody coming either way, and then I'll pull out, which is hard around here, right around, especially around campus. So, but it's the same principle. We are using our eyes to adjust how we're going to drive our car. So in that case, it's more of a hand-foot coordination, hand steering wheel coordination. But we use that all the time. We're always assessing where things are, how traffic is. Sometimes we assess pretty well, and every now and then we might assess wrong. So it happens. But this hand-eye coordination, we do it all the time. How do we know where our hands are? Our proprioceptors are telling us where the limb is, where our hand is. Our eyes are telling us where the object is that we're tracking. The proprioceptors tell us where our hand is. Our brain allows us to put the two together. The cerebral hemispheres allow us to put it together so that we can say, I must put my hand here. I track the object so I can catch it. And Cameron threw the markers at me, even though they were high, almost out of reach. It was a bad throw. I was still able to catch it. No, it was a good throw. I'm just, I'm just picking. So sorry. So yeah. So now, proprioception. We can't have hand-eye coordination unless we have proprioception, because it doesn't do any good to track the object if we don't know where our hand is. Are we going to go flailing around here? It's like watching a little kid, at T-ball, or learning how to catch, and or swing a bat, and you throw the ball, and then the bat goes up in the air, or it goes around behind them, or they throw the bat, or whatever. They very ever rarely connect with the ball because their muscles haven't learned yet. They haven't got the muscle memory of knowing when to swing and when not to swing. Some people never learn that. Yeah. Part of this then leads into reflexes. Now, a reflex, this is an important thing to remember because lots of people get this wrong because they don't read the questions properly on a test. That's just a big hint, by the way. A reflex is an involuntary, predictable response, meaning it will give you the same response every time. If you put your hand down on something hot, you're going to pull your hand back. That's a rapid, predictable response. You always yank your hand back at something hot. You step on something sharp, you will always, unless you have something going on, you will always yank your foot back. Now, later in AP2, we're going to learn all about what's known as neuropathy that your diabetic patients may develop. That's, we're going to leave them out of the picture for right now. So, normally, a person with a healthy nervous system, if they step on something sharp, will yank their foot back. It hurts. That's a reflex. So it is a involuntary, very rapid, predictable, meaning it will happen every time you do that. If we hear a loud noise in the hall, we'll all turn our head in that direction. That's a predictable response. If there's a bright, if we see a bright flash of light outside, maybe we're going to have a thunderstorm. We hit a nice bolt of lightning comes close to the building. We'd all turn our heads in the direction of the lightning flash, or when we hear the sound of thunder, we may turn in the direction where we perceive the noise coming from. Those are predictable responses. We do the same, we will, with a reflex, we will always have the same response every time. And these reflexes occur through the spinal cord. They don't involve the brain. Reflexes take place through the spinal cord because they're so fast, they don't involve the brain. The decision is made at the level of the spinal cord. The decision says, okay, you put your hand down on something hot, let's pull your hand back away from that. I'll tell the brain what's going on, but in the meantime, get your hand away. Why waste the extra millisecond or so that it takes to go up to the brain and say, hey, I got my hand on something hot and it's hurting. What should we do? And for the brain to turn on and say, well, I think usually you should probably pull your hand back. We would not be able to, to us, it would be an instantaneous response anyway, but it's faster to deal with at the level of the spinal cord. So reflexes are generally spinal responses. The brain is made aware. Excuse me. Thank you. The brain's made aware of what's going on, but the brain has no say in it. The brain has no say in yanking your hand back from something hot or pulling your foot away from something sharp. You step on a Lego in the middle of the night if you have kids. What a joy. You trade, when you have little kids, you worry about Legos. When you have dogs, you worry about other things you might step on in the middle of the night. Anyway, reflexes can be either intrinsic, meaning these are inborn reflexes. They're rapid, they're involuntary, they are still predictable. Posture is a reflex. You know that posture is a reflex. Visceral activities are a reflex. If your bladder fills up with urine, you're going to have to pee. That's a reflex. It's a slower reflex, but it's still a reflex. When you swallow something, when you put food in your mouth, you will automatically open up your esophagus there's a little ring of muscle controlling the opening of the esophagus called the esophageal sphincter. That's what a sphincter is, it's a ring of muscle. And as soon as you swallow something, two things happen automatically. Your airway closes so you don't put food in your lungs, and your esophageal sphincter opens up and food goes down the esophagus. It's automatic. That is a visceral reflex. When, let me think of another one. When you put fat in your small intestine, you will release bile from your gallbladder to chop up the fat. That's a visceral reflex. It happens automatically. We don't have to stop to think about it. We don't have to squeeze our gallbladder to get some bile to come out to go into our small intestine. So all of these are inborn reflexes. These are all motor responses to a stimulus. The sharp object, the hot surface, those are all inborn. Those are intrinsic. Now, a learned reflex comes from practice or repetition. Now, you may not know what a hot surface is. You may, as a small child, you may touch something that's hot that you don't know it's hot and discover that it hurts. Now, your normal reflex for a hot surface is to pull your hand back, or a sharp object is to pull your hand back. But the learned part of it is learning what is a hot surface. If you have one of those smooth top stoves, you don't have the old elements in there that glow anymore. Now you just have a surface with a little warning light. A 3-year-old's not going to pay attention to the warning light, and ooh, that hurts. Learned, acquired reflexes. They come from practice. They come from experience. They come from repetition. Driving is a whole series of learned reflexes. You don't pay attention to every aspect of your car when you drive. You pay attention to the road. You steer the vehicle. You press on the gas. You apply the brakes. But you're not paying attention to every, you don't have conscious awareness of what's going on. You don't sit there in the car with your hands gripped on the steering wheel, looking straight ahead with tunnel vision, afraid to turn to the left. Don't look like that. Afraid to turn to the left or right because you'll run off the road and explode. You don't think your car will explode, do you? Okay.
I have a friend who went off the road, though.
Well,
I always keep the lines.
that's perfectly normal. But there are lots of people though that's the only way they can drive. Our one son is so slow a driver. He thinks that anybody going more. He's 31 years old and he drives at 20 miles an hour. I can't wait to see when he's like at 80 how fast he's going to drive then. Probably negative numbers. So our other son is just the opposite. So he's driving at 80 now. I can't wait to see, instead of 20. So same age. But many times we go into our driving skill habits. Our reflexes, many times we're driving and our brain is somewhere else, yet we're maintaining perfect control of the vehicle. But how many times you've been driving and listening to the radio or talking to somebody, you're talking on your phone or whatever you're doing, and yes, you're driving along, you're doing just fine. The vehicle's in complete control, you know what's going on at all times, and the conscious part of your brain is somewhere else. You're thinking of something else. Consider coming down from Gatlinburg. How many times have you come down from Gatlinburg, get down almost to Pigeon Forge, and then say to the person that's with you, if you have somebody in the car with you, hopefully you're not talking to yourself, says, did we go through the tunnel? That ever happened? Yeah, okay. So, because if you're not, if you're just driving along and you're engaged in something else, Driving is a reflex. Did we go through the tunnel and you're pulling into, you're pulling into Krispy Kreme in Pigeon Forge? Oh, we missed the tunnel. Well, no, you didn't miss the tunnel. You just drove through it and didn't pay attention to it. So, which means that you were driving just fine. Driving is an acquired reflex. Practice in sports, playing, some sort of competitive game or even non-competitive games, baseball, football, softball, basketball, soccer, lacrosse, these are all games that require, sports that require practice. We get better with practice. We get better with repetition. If you play an instrument, if you use the keyboard on your computer or on your touchscreen, we get better over time. We get a new computer. We get better with it over time than what the first day you open up a brand new computer or a tablet or whatever, there's a little bit of a learning curve, and then you get better. That learning curve allows you to practice and practice and practice. How many of you have ever ridden a bicycle? Okay. There was a point when you were learning to ride a bicycle that it all came together, because riding a bicycle involves maintaining balance, maintaining speed as you ride the bicycle so that you don't fall over. There's a certain amount of, we call it centrifugal force, that you apply to the wheels so that you overcome the resistance from the road surface so that you don't fall over. You have to be pedaling fast enough to keep the bicycle upright so that you can go forward. And that's the whole learning curve, is trying to maintain that right speed so that you can overcome the resistance of the road and overcome the force of gravity. You didn't know it was complicated, did you? But once we learn to ride a bicycle, it doesn't matter how old we are, we always remember. That's one of those practice things that we may not have ridden a bicycle in 20 years, but we still remember how to. Driving is the same way. Driving skills are some of the last skills that we lose in muscle memory. Dementia patients who have been driving for 70 or 80 years may forget everything else. They may forget family members. They may forget where they live. They may forget what they had for breakfast that day. They may forget all sorts of stuff. But some of the last skills they generally lose are things that they have practiced and practiced and practiced for years. They can get in the car and they can drive for hours. They don't know where they're going, but they will do everything right, because those skills were embedded and stayed there for a long time. They're some of the last skills to lose. They are learned reflexes. Okay, now, reflexes are fast, a lot faster than this. So, again, this is also a combination of hand-eye coordination and reflexes. Reflexively, when someone throws something at us, we will throw our hand up to at least block it. That's a reflex. The ability to catch it involves tying in the proprioceptors directly to the eye motion. So this is another example of a learned reflex. To play professional baseball at third base requires the ability to process information rapidly. This is not okay, he hit the ball, it's coming towards me, I need to go over and knock the ball down. Then let's see, what should I do? I know, I'll throw it to first base. In the time it took me to describe what has to happen, he's already done it. Practice gives you the ability to do stuff like this. Practice and practice and more practice allows you to do this. It is a learned reflex. A person, a player generally can't do that the first time they ever play third base. There are always the anomalies, there are always the exceptions, but generally most people that are going to end up playing third base, even at a professional level, have to learn how to do that. So, it's just like driving, a learned reflex. What do you do when the light turns yellow? I know. And we're going to address that in lecture too. What do you do at a stop sign? Okay. What do you do when somebody runs in front of you, Cameron? Okay, he's 0 for 3 at this point. So you do stop when someone runs in front of you, right? Okay, good. Okay, I'll let you go on that. That's a reflex. Somebody runs out in front of you and you stop. Someone applies their brakes in front of you and you try very hard to stop. It's a learned reflex. When the brake lights come on in front of you, you have to stop suddenly because you're assessing a whole boatload of information you didn't even think about. So, okay. Now, a reflex has 5 parts to it. We call it the reflex arc. And it forms a nice little arc pattern that does not involve the brain. First, we have a receptor that gets stimulated. It can be touch, it can be pressure, it can be pain, it can be sound, it can be temperature, it can be motion. These receptors are stimulated and they send a signal on a sensory neuron. Sensory neurons always go to the central nervous system. In this case, the central nervous system is part of the spinal cord. Spinal cord and the brain make up the central nervous system. Here, we're going to use the spinal cord. We send a signal, an action potential on a sensory neuron to the spinal cord, and the spinal cord processes the information, and then sends a signal back out on a motor nerve to a muscle or to a gland. So we do something. If we get hot, we sweat. That's a reflex. We don't have to stop and think, oh, I'm hot, I better start sweating. That's a reflexive action. We go from the temperature receptor is activated. It sends a signal to the sensory neuron, which go to the central nervous system. The central nervous system processes that information because remember, the sensory receptor can't tell you what's happening. All it can do is get turned on. The sensory receptor is like a light switch. Light switch has no idea what's happening when it's turned on. It's either on or off. When it's on, it's on. It doesn't know that it's got lights it's controlling. Sensory receptor is just sending out action potentials. That's all. Those action potentials are processed in the central nervous system, in this case, the spinal cord, and a signal is sent out from the spinal cord down a motor nerve to a sweat gland, and we sweat, or to a muscle that says, pull your hand back. At the same time, we send a signal up the spinal cord to the brain and say, hey, by the way, I'm hot and I'm sweating, or I just stepped on something sharp, it hurts, and you might want to get a Band-Aid because it's bleeding. But in the meantime, I've moved my foot away from the sharp object. And it looks like this. This is a reflex arc right here. Oh, I've got a comment. Let's see. Oh, I understand. It's okay. So now okay, so the reflex arc. The stimulus, in this case, it's some sharp object stuck in the skin, activating either a touch receptor or a pain receptor or both. The signal is being sent down from the receptor to the spinal cord through the sensory neuron there in blue. In the middle of the spinal cord, in the gray matter of the spinal cord, which is brown in this case, but it's really the gray matter, what we call the butterfly of the spinal cord, is an integration center where we process information coming in. Because what's coming down the sensory neuron is an action potential. And all action potentials look alike. Only the integration center can tell us what the action potential means. And so it does. And it also dictates the response. And the response is sent out, another action potential goes out on the motor neuron to the effector. And the effector is the last part of the reflex arc. And it tells us to yank our hand back, or yank our foot back, or to sweat, or to shiver, or whatever our reflex is going to be. And this is the reflex arc. Now, at the same time, you notice on the cross section of the spinal cord, this area, the dark area, is called the gray matter. That is the butterfly area. That's where all this processing takes place. The white matter out here are all the axons of the spinal cord, and this integration center will send a signal up to the brain in the white matter, to go up the white matter to the brain and say, by the way, you know, I've got a pin stuck in my foot, and you know, you might want to pull it out. You know, I've yanked my foot back, I may be bleeding, whatever. So the brain is made aware of what's going on, but the brain had no impact on the response. No. Reflexes can be either somatic, and that somatic means skeletal. So anytime we see the term somatic, we're talking about skeletal muscle, or maybe on the surface of the skin. A reflex that activates a skeletal muscle is a somatic reflex. So yank your hand back is a somatic reflex. A visceral reflex involves smooth muscle, cardiac muscle, or the glands. I got to sweat because I'm hot. I got to speed my heart up or slow it down. That's a reflex. You know, we go climb a flight of stairs, our heart rate goes up. That's a visceral reflex. We swallow something and starting in our esophagus, we start squeezing the food to push it into our stomach. That is a smooth muscle reflex. It will always do that. So that's a visceral or autonomic nervous system reflex. So there's two types here. Now, and this is the patellar reflex. This is a test on the efficiency of the nervous system. If the nervous system is working properly at the level of the nerve that controls the spinal nerve that controls your patella, you take a rubber mallet and you tap, not smack hard, but you tap the patellar tendon. Now, the patellar tendon connects the femur to the tibia and covers the patella, the kneecap. And if you tap the tendon, what it does is it stimulates the quadricep muscles on the top of the thigh, and they think that the muscle is contracting. Rather, the muscle spindle in the quadriceps muscles thinks the muscle's contracting because you have, if you tap the patellar tendon, it thinks it's being stretched. And that tendon would only stretch if the quads were contracting. So what will happen is that will send a signal to the spinal cord. Spinal cord will process it and send a signal back to the quads and say, contract. Because if the tendon is stretched, the muscle needs to contract. And so if we get that patellar reflex, it means that our central nervous system, at least at the level of that particular nerve, is working just fine. If we don't get it to kick out like that, it might indicate there's something wrong with the conduction system. Now, usually what happens when we do this is it doesn't work, because hitting the patellar tendon at exactly the right spot takes a little effort. And some people hit high, some people hit low, some people have the hammer turned around the wrong way. I'm always reluctant to give people hammers to hit each other in class, but sometimes it works out okay. And every now and then you'll get somebody that does it just right, and the person they're tapping will kick their leg out. So And you know, the ideal, of course, is to get the leg to kick out, because what it's showing is that everything is being processed correctly. It looks like this. There's your patellar tendon right here. There's the kneecap. The patellar tendon attaches to the end of the femur and the top of the tibia. You hit the tendon below the knee, and that will stimulate these muscle spindles here. And because the tendon when the tendon is hit, it stretches. The muscle spindles think that the muscle has contracted, because why wouldn't it be contracting? If the tendon's stretched, that's what happens when the muscles contract. It pulls on the tendon when the muscles didn't contract. So a signal goes to the spinal cord that says, hey, you know, we're stretching, but nothing's happening. And so the spinal cord will process that information. Notice how it sends a signal to the brain there in that third blue line going up. It says to the brain, it's in the white matter. We process the information in the gray matter and send a signal back to the quads, and the quads kick out. At the same time, since we already believe we've contracted our quads, we send a second signal to the hamstrings and say, don't do anything. That's what the dotted red line is. So, you know, we get our contraction, but we don't get an automatic antagonistic response. We tell the hamstrings to relax. Because normally when if the quads contract, the hamstrings relax, and then the hamstrings will contract and the quads will relax. Here we want the leg to kick out. We don't want the hamstrings to do anything else. So it's a very simple test, but if it doesn't work, you know, when someone's doing it correctly, who knows what they're doing? If it doesn't work, it indicates that there might be something wrong at the level of that spinal nerve. So there's a whole series of non-invasive reflexive tests that you can do to give you the first idea that there might be something going on in the spinal cord. So anyway, that's everything on proprioception and reflex arcs and reflexes. And next week we're going to get into the special senses. We're going to take a look at the nose and the mouth and the ear and the eye and the brain. And then the following week, it will be brain and eyeball dissection. So, and I will see everybody on Thursday for lecture. Anybody have any questions on anything? Then I'm going to get us out of here.